Okay, so the last substance we're going to look at in terms of knowing what calculations you need to be able to do in the stoichiometry unit are gases. And so remembering that gases are gas molecules with the majority of the volume of gases occupied by space. A very important concept in gas stoichiometry is this idea of molar volume. So if you'll remember the ideal gas law, hopefully you can see that the volume doesn't really depend on what the gas is. There's no molar mass there. It only depends on pressure, temperature, and number of moles. And so what we can do is we can actually calculate the molar volume for very specific, useful to chemists conditions. So we basically talk about this idea of standard ambient temperature and pressure, also known as room temperature, sometimes shortened to SATP or RTP. And the basic idea is that no matter what gas you have at room temperature and pressure, or standard ambient temperature and pressure, they mean the same thing, which is 25 degrees Celsius and 100 kilopascals, or 100,000 pascals, the volume of a gas will be 24 decimeters cubed per mole. So no matter what gas it is, if you have 1 mole of our gas at SATP, it'll take up 24 decimeters cubed. The other value that chemists like to use is known as standard temperature and pressure, and so this is when the temperature is 0 degrees Celsius and the pressure is 100 kilopascals, and again, the volume for 1 mole of any gas is 2.7. Now again, you don't need to memorize this, as I've just highlighted there in the data booklet. Now taking a look at the ideal gas law, let's take a look and see what happens to variables as we change them. So taking a look at volume and pressure, if you imagine a balloon above the water at 1 atmosphere, it's normal size, but as you bring the balloon lower and lower, it experiences a greater pressure due to the water above it. So for example, at 10 meters, it experiences 2 times the atmospheric pressure. At 20 meters, it experiences 3 times the atmospheric pressure, etc. And so what will happen is the volume of the gas in the balloon will get smaller and smaller as there's more pressure pushing on the walls of the balloon. And so if you take a look at the graph, you can see that as I increase pressure, my volume decreases. And so we can write that as a formula as volume is equal to something times 1 over pressure. Similarly, we can take a look at volume and temperature. If we have a balloon over a candle and then crank that candle up so that it's giving off a lot more heat, what will happen to the volume of the balloon is that it'll increase. And so we can say as temperature increases, so does volume. And again, we can write that as volume is equal to some constant times temperature. The third pair that we're going to look at is pressure and temperature. And so again here, imagine instead of heating up a balloon, now we have a steel box with walls that cannot expand. And so if we were to heat up a steel box with a candle and we would increase the heat on that steel box, hopefully you can imagine that the pressure inside of that steel box would increase. Again, because that steel box is unable to change its size and expand like in the previous example. And so here we can say as temperature increases, so does pressure, and so we can write out our equation. Pressure is equal to some constant times temperature. Putting that all together, we get our ideal gas law, PV equals nRT. Now let me go through each of these different variables. So we have pressure, and the tricky thing here is you need to remember pressure is measured in pascals. A lot of the time IB will give you kilopascals. Just multiply that by 1,000 to get to you the number of pascals. Volume, again, volume is measured in meters cubed, which is an unusual unit. Usually IB likes to give you decimeters cubed, and so again, to get that to meters cubed, we divide by 1,000. N stands for the number of moles. No surprises here. It's just measured in moles. And then if you take a look at R is actually a combination of K1, K2, K3. All of those proportionality constants are combined into R, known as the gas constant, and that's given in your IB data booklet. It's 8.31. T, again, a weird unit, is given in Kelvin. If you have degrees Celsius, in order to convert it into Kelvin, you add 273.15. So again, the calculations here are not difficult. They're multiplying or dividing. The tricky thing here is remembering to convert to units that this equation requires. And again, it requires those specific units because of the units for the gas constant. Again, I'm showing you what you don't need to memorize. You can find a lot of these values in the data booklet.